All right, so good evening, everyone. Thanks for joining the session. I know this session is the last one between the parties, so we'll try to make it quick. So I'm from MapR in the product management team, mainly responsible for our SQL and Hadoop initiatives. So let me start with a quick context on what I'm going to cover in this session today, right? So most of you have seen this particular graph. So we know that data in enterprises is growing fast, and there is a structured data component to it and unstructured data. So if you see what is kind of contributing to the growth of the data, right? Structured data is growing fairly moderately, but it is unstructured data which is growing exponentially, right? The unstructured data could be your PDFs, images, like pure unstructured data, but it could also be application generated data, right? So this could be click streams, logs, sensor data coming up from something like Internet of Things. And most of the times this application generated data is in semi-structured data formats such as JSON, right? And more, this kind of data is getting persisted in non-relational, no schema data stores. So this could be Hadoop, HBase, MongoDB, Cassandra, etc. So what I want to cover in the session today is briefly about open source project called Drill. I don't know how many of you have heard about Drill, quickly. Okay, so we'll talk about this, a very high performance, flexible SQL layer to query and manipulate semi-structured data, complex data, and how you can leverage kind of the power and flexibility of Drill as part of the Spark programs that you write. And then briefly talk about what is the current status of the integration and what are kind of the next steps. So Drill, the way we like to describe that is it's a schema-free SQL engine for big data. Right, so the idea really is you point to the data and you start doing SQL queries. So you don't have to define any schema definitions, either in Hive Metastore or any other central repository. You just point to the data and you get up and running in minutes. And Drill has ability to access any type of data source. So data could be in files, it could be in Hive, it could be in HBase, or MapRDB, or it could be in Mongo, Cassandra, and there is a flexible kind of extensible storage plugin layer, so you can implement additional plugins. But the idea is bring the data from all these different types of data sources in a single query, you can combine them. And Drill has ability to work with simple data types, complex data types, schema-less data, so very flexible layer. We'll walk through a number of examples covering that. And Drill provides industry standard APIs, so it has ANSI SQL, it has JDBC, ODBC driver, so you can plug in with the BI tools, and it also has a REST endpoint if you're trying to build applications on top of it. It's designed for performance on scale, so I'm not going to go a lot of detail into the architecture, but it's designed for scale. So you can run it on one machine, thousands of machines, and you can scale it without having to hit any bottlenecks, either on the network side or on the processing side. And the last but not the least is extreme easy to use. So you just download it onto your machine. You don't need Hadoop. You don't need any prerequisites. You just download it onto your laptop. You point to some text file, JSON files, and you can start doing SQL queries in just minutes. So we'll walk through again a number of examples to make this more concrete. So the first thing to note is Drill is what one of the analysts calls it as OmniSQL. So there is a 3-point, I would say, the namespace for Drill queries. If you can see this, it says select star, which could be any SQL query. It's just simple thing is select star. And then there is something called DFS, so you can give it any name. But this is representing the data source in Drill, right? So you can, for Drill, you can query from a file system, right? It could be local, distributed, Hadoop file system. It could be S3 file system. And data could be in text files, Parquet files, JSON files, right? So file system itself is a storage plugin for Drill. Storage plugin is nothing but a representation of the data source. And if you have data in HBase, right, so that is one data source for Drill. Hive Metastore, if you have already populated Hive Metastore, you can do low latency queries on it using Drill. And then there is easy API to go beyond Hadoop. So there are some early stage plugins for MongoDB, Cassandra, there is a JDBC plugin in work. So basically all these data sources, Drill has ability to query from. The second part of the namespace here, what I have here in green as ELP. So we refer to that as a workspace. So if I'm querying a file system, the workspace is a subdirectory, right? So maybe I'm collecting all the log information in a logs directory on the file system. I'm collecting all the clickstream information on a clickstream directory. So this is nothing but a subdirectory on the file system. And if I'm querying HBase, the workspace is a namespace. If I'm querying Hive tables, then the workspace is a Hive database. And the third part is the actual table name. So with Drill, you can actually query files directly. So you just point your SQL query to a file, a directory, and you can start doing SQL queries. right? So again, the table in drill, it can simply be a path name to a file system. It could be a Hive table, it could be a HBase table, or any other data source that you work with. And very briefly on the performance, right? So I mentioned that this is a distributed SQL query engine, run it on 1 machine, 1,000 machines, depending on the number of users you want to support, that amount of data that you want to process, you can scale it out. And it is a columnar vectorized execution engine, so it's designed for interactive query performance, right? So drill is columnar both in storage as well as at the execution layer. So the in-memory data model for drill is a columnar hierarchical data model. So it can do all the standard SQL operations like joins, aggregation, sorting directly on top of the columnar data, right? Which is very efficient in terms of CPU as well as memory for certain types of analytic workloads. And it's an optimistic execution engine, so it doesn't use MapReduce or Spark or Tez. It has its own execution engine, right? Again, designed for complex data, designed for large volumes of data. And it's highly extensible. So the core daemon in drill is called drillbit. So if you want to run drill, basically this is the service that you would install. You can run it on some nodes in the cluster. You can run on all the data nodes in the cluster. But each drill bit has ability to take requests from the client. It has a SQL parser. It would generate a logical plan. And there is a number of cost-based as well as rule-based optimizations. So it will generate a physical plan. And then the execution layer would reach out to the data sources, again, all the different data sources that it works with, and then process the data, right? So it's an execution engine that is, again, MPP kind of an engine. And all the things in the blue here are extensible. So you can build your own storage plugins. You can build your own client APIs. You can plug in explicitly a JSON documented logical and physical plans that you can execute using drill. So what does it mean to integrate drill and Spark, right? So there are a couple of use cases. One is I'm going to show a number of examples on what is the kind of the flexibility and the power of drill, but you can use all that as part of Spark program. So you just basically point to drill, submit a drill query, you get the results, and you use them, you manipulate them using Spark programs. Another aspect is, again, you have the Spark RDDs, right, as part of the data pipelines, and you manipulate them using drill queries. Right, so a couple of data integration points, and I'll have, I think, a couple of slides just to show how it actually works. So let me walk through a few examples, and then I'll go into kind of the sample Spark programs. So the examples that I'm going to use is, it's a demo data set downloaded from ELP. It's called business.json. The interesting thing with this data set is it has a set of simple elements as well as complex elements. So if I look at it, it has business ID, it has the address of the business, it has the hours during which the business is open, and all the things in blue there, if you can see, they are all complex elements. So they could be arrays, they could be maps, and then there are also some simple relational type of elements. So this is one JSON we'll try to explore using drill. And another JSON is each of the businesses has got some reviews on ELP, right? So the reviews data set basically, again, has information like who is the user doing the review, and what is kind of the star rating they gave, what is the date of the review, and the votes, again, as you see in the blue here, it's a complex elements. So it is identifying how many people rated this particular review as funny, cool, interesting, whatever, right? So this is a map. And then downloading, again, you can work with drill extremely easy. So before you start to play with Spark, basically you can download it and you can start playing with it. So it's, you downloaded the tar file, and there is a SQLine application, which is a JDBC application that comes packaged with drill. So you just launch it in the second step, and then that's it. That's it. You can start writing kind of SQL queries. So in this example, I'm trying to figure out basically what are the top businesses per state, right? Per state and city. So it's a very simple SQL analytic statement. Again, I'm pointing to the JSON file and I'm starting to do SQL queries, right? I didn't need to do any setup to do this. And the drill has ability to expose the directories as partitions. So this is the example where I'm gathering all the sales data, let's say on my file system, and the data is organized in years, and within each year, I have quarters, right? So 2014, 2015, 2013, and within each year, I have the quarters as, again, the next level of partitions. So with drill, it exposes all these directory structures as dynamic variables. So as you see in the query, I can say select dir 0, dir0 is basically representing the top level directory. So in which case this is the year, right? So the 2014, 2015, it is exposed as dir0. And then the dir1 is representing basically the quarters within that particular year, right? So very, very easy kind of exposing the partitioned structure on the file system as a dynamic variable in the query so that you can start manipulating it. So drill is all about using the data in a very easy fashion and exploring it using SQL. So the next aspect is drill has ability to reach into complex data. So this is an example where I'm trying to figure out what are some Mediterranean restaurants open in Las Vegas around 10 o'clock in the night, right? So if you see the query here, it has things like b.hours.friday. So it simply uses the dotted notation in order to reach into the complex elements. And you can go to any level of nesting, right? So here I can see b.hours.friday.open. So you can reach into any level of nesting and you can do filters, you can do aggregations, you can do joins. So basically very easy, very intuitive way to get into the complex data. And one of the SQL extensions that drill has here is repeated contains. So as you saw here, as you saw in the example, each business is listed under multiple categories, right? So this is trying to figure out, does that category array have a string called Mediterranean, right? So it is trying to use a simple function, repeated contains, to figure out if that string exists, then return me that particular row. Right, again, to do this query, I didn't have to do any ETL, I didn't have to do any flattening, just point to the data and start doing the queries. And you can leverage all this as part of the Spark program. And drill is ANSI SQL compliant, so all the standard SQL query functionality that you would expect, joins, aggregation, sorting, all the standard SQL data types, intervals, correlated subqueries. So the natural way to work with SQL, all the syntax is available as part of drill. So this is just an example, again, showcasing kind of the SQL aspect of it. And once I understand a little bit about the data, I see the structure, I have an understanding of how can I leverage this data, I can do standard things like I can create a view, for example, right? So in this example, I'm trying to combine the data from business.json, review.json, and I'm creating a view on top of it, right? And if you see the create or replace view, the syntax, it has dfs.tmp.businessreviews. What essentially it is doing is, DFS is just my file system. In that, TMP is a workspace. So it's just pointing to a temp directory on my machine. And it is creating a view, which is nothing but a file on my file system. So it's simply decentralized metadata. There is no centralized metadata requirement. And this is just, if I go to my file system, temp directory, I see a file called businessreviews.view.drill, right? So it's creating a .drill file. And views are a natural kind of way to manage the data. So if you want to provide more granular access, if you want to provide row level, column level kind of security permissions, this is kind of the unit that you would use. And you don't need another security repository because you are using the file system permissions, again, to secure these views as well. And you can create tables. So in this example, I just set up the storage format as Parquet, and then I can create a table, right? So the result of this particular statement is a Parquet file on my file system. So again, I didn't need to do any Hive metastore. I didn't need to set up anything. This is just creating self-describing Parquet file along with the schema. And I could set up the storage format as JSON. I can set up the storage format as text files. Again, there is a lot of flexibility. And the whole idea is you explore the data and you are able to persist some of the insights which you think could be repetitive as views, logical views, or actually physical kind of files. And this is where the interesting part comes in. So far there is ANSI SQL, there is interesting ways to access the data, but drill also has a number of extensions to actually manipulate the complex data. So this is an example, again, going back to kind of the categories column. So each business in the first query has name, and each business, again, is listed under a number of categories. So what the second query is trying to do is I'm trying to flatten the data dynamically, right? No ETL, nothing is required. I just flatten the data using the flatten function, right? So for each category of the business, the flatten function would generate a separate row. So the whole idea is you're trying to kind of create a relational form of the data so that you can use additional kind of analytics, additional kind of manipulation, or you can visualize from the BI tools. This is a very simple example of flatten, right, where I'm simply manipulating a array which is of scalar values using flatten. But imagine if I have a 8-level nested structure. So I can do flatten on top of flatten, flatten next to flatten, so you can navigate and reach into any kind of complex data just by using this function. So this again, like there are lots of extensions like this, but this is just building on top of the result of the flatten. So I'm trying to figure out what are the most common categories under which the businesses are listed. So I'm taking the output of flatten and I'm computing what are the most popular categories, right? So this is something which is very hard to do. And again, I'm doing it without any ETL, without any prep required. And drill works with self-describing data, right? So some of the data formats like Parquet, JSON, they have some level of schema information available. So drill can leverage that. But if drill is querying HBase doesn't have any data types. So drill provides a set of functions called convert from and convert to. So convert from, what it is doing is it is trying to interpret the data. It is telling drill to interpret the data in a particular encoding. So there are around 30 or so functions available. But this particular query, what it is doing is, in the HBase storage plugin, I have a table called donuts. And one of the tables, the donuts table has a column family called CF1. And one of the columns in that column family is donut.json. And all it is trying to do is telling drill, interpret this particular column value as JSON, because HBase doesn't have data types and you need something to work with the data. So it is interpreting it as JSON, and once you have the JSON document out, again, you can do all kinds of manipulation using the power of drill, directly working with the JSON documents. So working with the dynamic columns is another important aspect. I don't want to go into a lot of detail here, but this is an example where same Yelp data set, it has check-in information. And the interesting thing with this particular data set is the check-in info column that you see here, it has dynamic set of elements. So this has information on between so and so duration in a day, right? So for example, 0-0, what it is saying is in the midnight from 12 o'clock to 1 o'clock on a Sunday, how many check-ins have happened. So a business might have check-ins at different times during the day. So the list of columns that you would get as part of the check-in info are dynamic, right? So this is a very actual, again, a simple use case where the number of days in a week are fixed. But imagine this in a sensor kind of situation where you have thousands of sensors deployed all over the world, and you might be getting this information from any of the sensors, and you don't want to define all the permutations and combinations of these columns. So this is, again, an example where the column names themselves are dynamic. So drill has a number of extensions, again, to work with some of this dynamic column data. So one of the functions, you can refer to this in the documentation, but one of the functions available is what we refer as KVGen. It's like key value generator. So it is taking that dynamic map, and it is converting into a very wide set of array of key value pairs, right? It's converting into key value pairs. And once you have the array, you can apply flatten on top of it, and you can do analytics on top of it. So in the next example, I'm trying to do how many check-ins have happened between so and so time duration on a Sunday. So to do this thing, again, imagine like how many relational tables that you have to generate to process this kind of data. And drill's power flexibility is, again, working with schemaless data, working with unknown dynamic data sets which keep changing, and without having to maintain a centralized schema definition. So what does this mean for Spark? So all the power, like some of these extensions to ANSI SQL, some of the ANSI SQL capabilities themselves, they all you can leverage them as part of Spark programs. So this is one of the queries that I had earlier, where I'm trying to get information from the business on give me only the restaurants, right? Repeated contains, the categories has restaurants. So you do a query like that in the Spark program, and there is something called drill RDD. So the drill RDD is what you would create, right, by pointing to the SQL statement. And once you have that result, again, you can navigate into the complex elements. So r.name, r.full address, r.hours.friday. Again, all the kind of power of drill is available within the Spark program, right? Subsequently, let's say once you got the results, you want to apply some machine learning on it, you want to do all the power of Spark, right, which is applying kind of advanced analytics, you can do that on top of the result in the data set. And another example here is this is querying a simple JSON document, but think about combining the data. Let's say I have all my log information in file system, I have all my master data in HBase, I have all my transactional information in Hive table, and all I have to do is write a single query, right? I don't have to do any programmatic way to represent this. I just write a single query, combine all the data from these 3 data sources, bring it into Spark, and you apply whatever additional kind of analytic things that you want to do in Spark data pipeline, right? So that's one example where drill query is input to the Spark job. The next one is once you are within the Spark context, again, you can use drill to query the data on the Spark RDDs. So this is an example where C object, again, is an interface which captures the JSON data model. It gives you an easy-to-use interface to interactively work with the complex data. So in this example, I'm trying to create a map for few numbers. Basically, take each number, square it, and create a map, right? Create an RDD. And then I register it as a table, and I start querying it using drill. Right, I mean, all the kind of standard paradigms of Spark that you're familiar with, but you can also combine it with the flexibility that it brings along. And once you, again, you query, you create drill RDD, and you can work with the data in whatever fashion that you want. So the idea is that drill is focusing on particular aspects, right? The flexibility is the core focus for drill, whether it is discovering schema on the fly, whether it is providing SQL extensions so that you can work with the complex data. And drill also has a powerful API to build user-defined functions. So you can do user-defined scalar functions, user-defined aggregate functions, and it is very easy to build. There's a bunch of documentation available. So again, the power of UDF. So it is flexible. And then the second part is rich storage plugin. I mentioned it has file system, Hive, HBase, Mongo, Cassandra, and the ecosystem is growing pretty quickly. So bring in all the data from all these data sources in a single query, right? And then columnar execution. It is designed for performance. It is designed for interactive queries. It is designed to work in a highly concurrent situation, right? And then ANSI SQL, we covered that briefly. On the other hand, Spark has the advantages, which is I have been listening throughout the talks in the day. One key point for Spark is it's extremely easy to use, right? So Python, all the different APIs that are available, and Scala API. So you use all the standard kind of easy to use APIs in the Spark programs. You leverage all the generalized processing, advanced analytic workflows, machine learning, all the power of Spark, and you combine that with the flexibility of drill, and that's the Spark program you can write. So where are we with respect to the integration? So some of the examples that I have shown, they're actually working examples, right? Functional integration is complete. The beta will be coming soon in next few weeks. In terms of next steps, there are a few areas we identified that need further improvement in efficiency. So between drill and Spark, there is data going back and forth, right? So drill is an off-heap columnar data model, whereas Spark is currently on-heap, row-based model, right? So between when you try to convert the data between each of these systems, there are some serialization efficiencies that need to be improved. So there is some work in progress that's happening in the community. And again, the idea is that the beta for this particular integration will be coming soon, and the community together will be working on improving the efficiencies. Both Drill and Spark are memory-intensive engines, so we need to work more on the memory efficiencies part as well here. So any questions, feel free to send email to the user alias drill@apache.org. And if you are interested in contributing, send email to the dev. So if you are interested in just trying out Drill as is, right? So Drill is an open source project. The current version of Drill is 1.0. It's just very recently, in the May 2nd week, it has gone into GA, generally available production release version. So you can just try it out. So there is some on-demand free MapR training. There is a test drive on Amazon. You can just launch a 5-hour free cluster and you can try out Drill. And then there is also a sandbox and a tutorial associated with it. So you can download it. It comes with preloaded data sets and a tutorial. Again, you can hands-on, you can try it out. And working with Drill, again, is extremely easy. There is a guide called Apache Drill in 10 minutes. It actually takes 2 minutes to go through that particular guide, right? So you just install on it your machine. You can start doing SQL queries on files. Or you can, if you already have a Hadoop cluster or any other cluster, you just download it onto your machine on the cluster. So there's a lot of documentation available. There are 12 or so tutorials available. And again, the documentation continues to improve in the past few weeks. So feel free to refer to the documentation and send any questions that you have to the user as well as dev alias. That's all I had to say. Thank you. Do you have time for questions? Yeah. Maybe we can take a couple of questions and then I can take offline.
Hello. So I have one question regarding the coexistence of drill bits and Spark executors on the same machines. So if you look at the execution model of one job in Spark, integration with drill, usually it would be some drill workload, then some Spark workload, then some drill workload, mutually exclusive most of the time. The most efficient thing would be to have drill bits and Spark executors on the same worker nodes in the cluster and utilize the CPU on and off between those RDD transformations. Is that something you've thought about, and have you resolved this? Is it able to coexist? Have you tried it?
Yeah, so I think that's just one point. We haven't necessarily gone into the architecture specifics, but the idea is that drill bits and Spark executors, they coexist, co-located on the same data nodes in the cluster, because that's the way to achieve data locality, right? Because drill will be sending data to Spark, Spark will be doing some processing and will writing it back to drill. So there is data flowing back and forth, right? So data locality is a key part, and one way to significantly achieve that is by co-locating them. Right, so we have done some experiments. Again, that is the area where we have identified some inefficiencies with respect to serialization, but that's where the work is happening. But certainly, they have to be co-located for better leverage.
That's great news. Thank you.